Okay, guess we'll get started. Good morning, everyone. This morning, privileged to have Mr. Alexander here give a talk on radiation effects. He's done many years' experience on a variety of disciplines, one being radiation effects on electronics and mitigations. Also assisted us in with a component to be flown on Trailblazer, a decimeter, and one to hopefully fly on another project we have called SATS. So, Mr. Alexander.
Okay, thanks. All right. Brian said I'm Dave Alexander, and talk about a number of things this morning. Kind of go from the gigantic to the infinitesimal. So it's kind of a large range of things to look at. Give me an idea of who I'm talking to. How many undergraduates do I have? Okay, and how many who are not double E's? Okay, so three.
I got a mech here.
Mechies.
Yeah.
Okay, Mechies. Okay. Okay. I'll have some things where I've tried to give you a little background in the double E side of it, and please feel free to ask questions. I'll either be able to answer them or I won't, but we'll be able to go through that. So we're going to talk about electronics in space, and in particular failure mechanisms that are associated with electronics in space. And really most of the issues associated with radiation have a lot to do with the sun. So that's the reason I put the blue sun on there. I thought it was kind of pretty, and so that's the background. But so solar radiation is a big part of what we experience in space. And so we'll be talking about that and its interaction with electronics. So as I say, please do stop me at any time, ask a question, and we'll go from there. Okay. Put a few refresher things in there on electronics for the undergrads and folks that aren't double E's. We'll be talking about reliability and lifetime. And if you're just putting a satellite up for 6 months, 3 months, 6 months, things like that, probably not a big issue, but many of you, I think, will probably go on to do longer-lived satellites, more complex satellites, and it doesn't matter when you are flying a mission whether your parts fail because of radiation or they fail because of reliability or longevity issues. The parts still failed. So I see those things as playing in together. We'll talk a little bit about the environment, and under that we'll talk about how that affects the electronics from single event mechanisms, so things that happen just kind of one count at a time, to total dose mechanisms, which are more pervasive and build up as you go along. Then from the reliability standpoints, we'll talk about NBTI, which is negative bias temperature instability, and we'll see how that is particularly a worrisome issue for modern electronics. Talk about hot carrier mechanisms, also something that's of concern with breakdown mechanisms, and we'll talk a little bit about the implications for future space systems and projects. So several things to talk about. What I have tried to do is make it a mechanism-oriented talk. Technology changes, and I'll try to show you there's been a lot of change in technology over the years that I've been involved with electronics. But if you have an appreciation of what the physical mechanisms are, those by and large stay the same. Their manifestations may be a little bit different as you go along, but the mechanisms help you if you can keep focused on that. Those mechanisms interact with the materials in different ways, and so we'll try to talk a little bit about how that interaction occurs. what the manifestation of the effects are. So if you have electronics, what's it going to do? How is it? What part of it's going to quit working? Is the gain going to change? Are the propagation delays going to change? Those sorts of things. And then finally, we'll talk a little bit about mitigation approaches. So what do you do? Is there anything you can do to protect your electronics, and what's going to be the impact on systems, or the implications for that? So we'll try to run through all of those things this morning as we go through each topic. Okay, so let's talk about radiation effects. As I said, the sun has an awful lot to do with the radiation effects that we encounter for satellites in Earth orbit. And that actually has a lot to do with anything that we send out within the solar system. Probably the thing that's most pervasive and constant is the solar wind. So you have a solar wind that streams out from the sun in all directions. It interacts with the magnetosphere around the Earth. We're all really happy that we have a magnetosphere. If we didn't, we'd be like Mars and have very little atmosphere. So the solar wind is a constant thing. But there are also what you might call solar storms associated with coronal mass ejection. So every once in a while, since the sun is spinning, it twists the magnetic fields associated with the sun, and when those twist or break, you tend to have an ejection of mass particles coming out of the sun, mostly protons and electrons, but some other heavier ions as well. So we'll talk a little bit about coronal mass ejections. They interact with the Earth's magnetosphere, and you've all heard about the Van Allen belts. So you have inner belts and outer belts composed of protons primarily for the inner belts, electrons for the outer belts, and everybody's heard about the South Atlantic anomaly. Ken?
This is a silly question.
Okay.
But you're an expert, at least compared to me. When we talk about the South Atlantic anomaly, I've always viewed that as not consistent. I mean, it changes all the time. Mm-hmm. Sometimes it's more horrific. Other times it decreases in magnitude or different effects and whatnot. Am I incorrect?
No, I don't think you're incorrect. The belts and the South Atlantic anomaly, we'll talk about that in the picture a little bit later.
Oh,
but the South Atlantic anomaly is really part of that inner proton belt, and it just is the South Atlantic anomaly because the magnetic pole is offset by, 11 to 15 degrees or so from the Earth's actual North Pole. So because of that, you have a dipping of that inner proton belt in the vicinity of at the South Atlantic anomaly. Now, the belts, the inner and outer Van Allen belts are relatively stable. If you get a huge coronal mass ejection come through, well, those particles come in, they get trapped, they interact with the Earth's magnetic field. Sometimes you get a third and sometimes a fourth belt that will form temporarily.
Oh, really?
But those, decay over time, over the course of a year and a half, something like that. But you can have those intermediate belts form, and that, of course, affects the dose that you get in your satellite if you happen to be at that altitude. But the proton belt and the electron belt, the inner and outer belts, are relatively stable. They'll get an injection if you have a coronal mass ejection, but basically they come about because you have protons or electrons coming through, they interact with the Earth's magnetic field, and they gyrate around the magnetic fields that connect the poles. and so they actually bounce back and forth between northern hemisphere and southern hemisphere, and they remain fairly stable from that standpoint.
Thank you.
Okay, so that's the solar contribution to the radiation environment. There are also galactic cosmic rays, and those originate outside the solar system. Most likely are probably associated with supernovas, either ancient or modern. And so they have a contribution of much heavier ions, and those ions are very, very energetic, and so it's very difficult to shield them. And we get some benefit. We get a fair amount of benefit from the Earth's magnetosphere because it deflects them. So satellites that are in relatively low Earth orbit don't interact so much with galactic cosmic rays. But those that are out at GPS orbits or geostationary orbits very much interact with the galactic cosmic rays, and they're very energetic particles and penetrate spacecraft, electronics, pretty much everything. So we'll talk about those two classes of radiation contributions. Okay, so let's talk a little bit about the solar wind. It's primarily protons and electrons, and that boils off of the sun. A small percentage of a little bit heavier ions, helium or alpha particles, oxygen, and a few other trace elements that have gotten incorporated in the sun and get boiled off. We see solar wind waxes and wanes with time, depending kind of on the order of sunspot activity that you have. You have a solar minimum that where you don't have very many sunspots. The solar wind comes off primarily at the solar equator, and it comes off around 400 kilometers per second. So not that that's a slow speed, but compared to the solar max, where you begin to have sunspot activities, and that grows typically from the sun's equator toward the poles, and the solar wind begins to be ejected near the poles, and it comes off almost twice as fast as at the low rate. So that's the 11-year solar cycle that you've heard about. So the solar wind and the amount of electrons and protons associated with that wind waxes and wanes over that 11-year cycle. So if that's the solar wind or solar breeze, the coronal mass ejections are like the solar hurricane. And as I said, they're associated with very heavy solar sunspot activity, the twisting of the magnetic fields as the sun rotates, and you can have large ejections of materials. On Earth, we see those as spectacular auroras. So if you see aurora far down into the northern hemisphere, it's probably associated with coronal mass ejections. You also have interaction with the long line power systems, and I think you've heard probably there have been times in the U.S. and Canada where large transients on long line power systems. So they are a major threat to satellites that are not hardened against radiation effects. So you can have loss of satellites. Those satellites that are out in geosynchronous or even further out are particularly susceptible because they aren't protected by the magnetosphere. And the magnetosphere itself, when you have a huge coronal mass ejection, is compressed toward the Earth, and is less effective in shielding some of the satellites at mid-orbits. So coronal mass ejections are a big deal, and there's a lot of work these days in monitoring space weather and giving early warning that coronal mass ejections are coming.
Excuse me, Dave.
Mm-hmm.
I'm trying to put this in perspective. Looking at this from a radiation hardening aspect, we always like to take and relate everything to to that. Does the solar wind have some sort of an average compared to that, or am I thinking entirely in the wrong context here?
No, the solar wind comes off in times of little activity. It comes off about 400 kilometers per second. In terms of the density of protons and electrons, I don't have that right off the top of my head, but there is a difference in density of the solar wind between solar max and solar min. And certainly there's a very large density difference in a coronal mass ejection.
Thank you.
Yeah, so that's not very quantitative, but I don't recall that right off the top of my head. Okay, so the belts, the inner belt is primarily protons. So if you're at relatively low Earth orbit, you're probably associated with the inner belt. It goes out here about. This is the Earth. So there's it's one Earth radius, and the inner belt goes out about 1.5, sometimes 2 Earth radii. So the Earth radius of the Earth is about 6,400 kilometers. So it goes out, a fair distance. So the satellites that we often talk about putting up here at COSMIAC, we talk about 200 kilometers, 400 kilometers, etc. So in a lot of those, we're actually under the belts. So except for where the belts dip down, and that's the South Atlantic anomaly. So you can begin to pick those up probably 200, 250 kilometers, pretty close to the Earth. And the inner belt proton energies range 100 keV to 400 MeV. 400 MeV is pretty energetic proton. The South Atlantic anomaly, since it dips down toward the atmosphere, the energy of the protons are a little bit less there, so they're in the 10 MeV range, and electrons in like 1 MeV. See?
Yeah, Dave, I understand we're going to have this weird thing happen over the next 50 years where the magnetic dipole, the principal component of the magnetic dipole is going to go away.
Yeah.
We're getting other navigation instruments just in time because all our old compasses are going to be worthless.
Right.
How is that going to affect, in your view, the structure of these belts and the South Atlantic anomaly and so forth?
Well, the belts themselves, as long as we have a magnetosphere, as long as the iron in the
magnetic field will have the same
yeah,
while it reverses.
right. So as long as we continue to have the magnetic field, the magnetosphere will have the belts.
Yeah.
But as that magnetic pole shifts or goes away, the South Atlantic anomaly is due to the fact that there is a 11 to 15 degree offset in that, and as that changes, then the South Atlantic anomaly will drift around. Okay, so It just depends on how far that the pole gets offset from the true.
My understanding is it's going to go away for a period of time, and you're going to have secondary, higher order terms.
Yeah, it's going to. I'm not sure anybody really knows. Okay, but when it happens, I guess we'll know.
Yeah.
But it will have.
A problem, right?
Yes, it will have an effect on the South Atlantic anomaly. Absolutely. Okay. Probably the South Atlantic anomaly came into the popular literature and all Hubble spacecraft. So Hubble went right through the Atlantic anomaly, and the number of upsets that they had was very significant. So you can go to several different sites and look at people have logged the number of upsets in their memories and devices with the position in orbit, and you can trace out the South Atlantic anomaly from those upsets. So it's a very, very real region. The second belt is primarily electrons, and it extends out probably 5, maybe 6 Earth radii. If you're flying solar cells, that's especially something to be concerned about. And it's much larger than the inner belt. Okay, let's talk a little bit about galactic cosmic rays. The composition of galactic cosmic rays are somewhat different than what you would expect from looking at the solar environment. First of all, they're primarily protons. Okay, so there's a lot of hydrogen in the universe. So of course you would expect probably a lot of protons, which are just hydrogen ions. Also, a fair amount of alpha particles. Again, helium's very pervasive in the universe, so you expect a lot of alphas. The rest of the ions are much more lightly represented, and only about 1% are the heavier ions. So if you look at the relative abundance of the different elemental ions in the galactic cosmic ray spectrum, you find a lot of hydrogen and helium up here, and then it drops off about, 4 orders of magnitude or so, and you pick up some of the other lighter elements and kind of end up with iron out here in terms of having a lot of abundance. So if you've looked at NASA specs for heavy ions, you'll see that they tend to say we're concerned with heavy ions up to iron, and after that the abundance drops off to the point where they're not really so concerned. So these are the elements that are forged in stars. So iron, I believe, is the last element that is the result of stellar fusion, and so you can kind of see that represented in the abundance of those materials. Okay, so have this kind of abundance. So what kind of energy do those elements impart to our electronics? And if you look at them from the standpoint of the amount of energy deposited, this axis here is dEdx. So the energy loss as you go through the material. This is silicon that we're interested in from an electronic standpoint. So you'll notice a couple of things. First of all, this is the ion energy down here. So if you looked at the amount of energy loss for a particular ion in silicon, that depends on what the energy of the ion is. Okay? So just because you have a more energetic ion doesn't mean that it's going to give you any more energy deposited in your material than a less energetic ion. So it depends on that linear energy transfer as to how big of an effect that any particular ion has on your electronics. And you can see there's some overlap. So if we were to pick a DEDX of 1, you could get that either from a low energy oxygen, a higher energy oxygen, helium, or you can't get it from a proton. But different ions can give you the same energy deposition per unit length depending on their energy. So if you want to analyze the potential effect of the galactic cosmic rays on your electronics, an easy way to do that is to look in terms of the linear energy transfer, okay, which is just the energy deposited per unit length. So DEDX and linear energy transfer are essentially the same thing. Physicists talk about DEDX. Engineers tend to talk about linear energy transfer. They're actually the same thing. So if you plot it in terms of the same linear energy transfer, okay, this is LET, okay, so I'll probably say LET a lot. That just means linear energy transfer, which means DEDX, change in energy with distance. Okay, so if you plot all the same LET, you get these kinds of curves. And you notice you have a difference between solar minimum and solar maximum in terms of the flux of the different linear energy transfer associated with the different ions. Okay, so why is that? Okay, well, the solar wind has a big effect on galactic cosmic rays. If you have a solar maximum where you have a lot of solar wind, then that tends to push galactic cosmic rays away from you. Less activity, you get more coming in. Okay. So if you see, you use the relative flux from those at the different LETs for your analysis, and you can look at the fluence associated with each of the different materials that we've looked at as a function of the different LETs here. So this guy gets transferred down to that kind of plot if we're looking for interaction with electronics. Okay. Now, when I went through this last night, I introduced this before I had introduced one of the concepts, but we'll work with it anyway. The question that engineers always have, well, how much effect am I going to get? How much environment am I going to have? Okay. There are codes that you can go to that are off the internet. One of them is called Cream 96. It's maintained now by Vanderbilt. It's a whole series of codes that are associated with that. And for your particular orbit, you can give it the orbital altitude, the inclination, a few orbital parameters, and it will give you the kind of environment that you can expect for your spacecraft. There's also a code called SpinVis that's maintained by European Space Agency. SpinVis has the AE8, the outer belt electron model in it. The Cream 96 does not, but other than that, they're pretty similar. There's also a series of codes associated with those. But without going through all of those simulations, you can get a kind of figure of merit, or a first cut at what your environment is going to be from this IEEE standard 1156.4. So what they've done is gone through and looked at a number of different orbits. They've classified them into 4 categories that you see here, and these are specific missions that have flown in each of those categories. So you see GPS-2 down here. And so they've tabulated all of the orbital parameters for each of those missions. So the first thing that I always do when somebody comes up and says, well, how much radiation am I going to get in a particular orbit, I go to this and I say, well, you know, you fit somewhere in here. And then if you look at the plot that they've developed, they give you a annual total dose. Okay, so an annual exposure of your spacecraft or your electronics for the 4 different levels of orbit that they had on this previous page.
Excuse me, Dave.
Uh-huh.
There's the confusion I've created in my own mind.
Okay.
But we take a look at these levels. Being unclassified as an unclassified question, do those levels relate to the Haynes standards?
No.
Thank you.
Okay, so if you were to pick the, if you say you were interested in International Space Station orbits 370 to 410 or so kilometers. Okay, so you could come up and pick one of these guys in the level 1 orbit, and then you come over here and you say level 1, depending on how much shielding I have, I can get an idea of what the total dose is for that orbit over the course of the year. Now, one of the things that I like about this is that they have done those calculations for you, and they've added in a factor of 2 design margin. So there's a factor of 2 in each of these plots. But it's a very easy way to give yourself an idea of what kind of environment you're going to see. And it's done in terms of shielding thickness of aluminum in mils. So if you had 100 mils of aluminum is a typical kind of shielding for a satellite. In fact, a lot of calculations are done in terms of that. So if you were in the level 2 orbit for a year, you could expect about somewhere a little more than probably 10 to the 4th, 10 kilorads in a year. And we haven't talked about what a rad is, but we'll talk about that later. For right now, it's just the exposure that you get from that kind of orbit. Okay. So let me recommend that 1156.4 to you. Something good to keep in the back of your pocket. Okay, so what kind of parts are we going to see in a satellite? This pie chart is from back, I think, around 2000, and they've gone through and tabulated the different kinds of parts that are in there. One thing that strikes me about this is we talk a lot and think a lot about advanced microelectronics and microprocessors and FPGAs and all that are on the cutting edge of electronics. But if you look at that, they really represent pretty small percentage of the total electronics that are in a satellite. So you have a lot of discrete devices, analog and digital small-scale integrated circuits that are there. So it's not, everything is not cutting edge, and so some of the things that have less robust performance from a radiation standpoint are very much used in satellites. So where is that going to go in the future? I think Ken and I talked about this a couple of years ago, and we said, well, probably things are going to go, 50% FPGAs and catalog parts, maybe 15%. I'm not sure I believe that any longer. It seems like it's taken longer to transition some of the advanced electronics into satellites. But we are going to see, I think, a continued reduction in the number of parts just because the piece part budgets are constrained. Civilian commercial technology is going to march on. We're going to like more and more of those things. Development time for small satellites will probably be compressed. There's always a need to drop power down, so a lot of the older technologies are rather power hungry, and people just want to do more things in smaller volume. So may not happen in the next 10 years or so, but I think we're moving toward that kind of mix of parts in the future. Okay, so for the MEs and folks, I thought I'd put in a couple of slides here just to give you a little background in electronics, and you've probably seen this before. Okay, there's basically two kinds of electronics we're going to talk about today. One is bipolar technology, and the other is MOS technology. Okay, bipolar transistors are you can think of them as putting two diodes together. Okay, a diode conducts current in one direction and blocks current in the other direction. Okay, so if you have a concept of, well, I'll just take two diodes and I'll put them together, and if I make the base, the two parts of the diode that come together, if I make that very small, and I give myself the ability to inject charge in here to try to turn this part of this section of diode on, if I make this small enough, then I can get current that starts out here but goes all the way through the device. Okay, so with a little bit of current put in here, I can control a lot of current that goes through there. Okay, so that gives me I can either have an NPN transistor, or I can have a PNP transistor, depending on how I put them together. So you can think of a bipolar transistor as a couple of diodes stuck together, but engineered so that we kind of fool the carriers to not stopping in the base of the device. If you look at it from a discrete transistor standpoint, this says simplified IC NPN transistor circuit. It's really not. I don't want to put that up there. Here's how you do it. Okay, you start off with a N-type material for this NPN. Okay, so that would be the collector down here. It's big, so it's going to collect all of the minority charge carriers. Okay, you put a base in here and you make it very thin. Okay, so that when charge carriers come across that junction, they essentially overshoot and come down and get collected in the collector. And this guy up here is the emitter, which has a large excess of charge carriers. So by changing the voltage across the base emitter, you inject charge carriers out of the emitter. They overshoot the base and get collected in the collector. And so with a little bit of modulation of the base voltage and current, you can control a lot of current through the collector and emitter. That would look like a discrete transistor. There's a lot of discrete transistors in satellites. Okay, that same transistor function also gets built into integrated circuits. So now here's my emitter. Here's my base. I have to make all my contacts up here on top. So I contact the emitter up here. I've got to come over here to contact my base, and then I've got to come all the way over here to contact my collector. And so, since that collector is fairly high resistance, I want to put a little parallel path down here so that it doesn't, I don't drop so much voltage across here when I'm going over to the collector. All of that has to be built on something, and it gets built on a P-type substrate. Okay, and to isolate it from other transistors, you have a couple of P diffusions down here, so that this becomes a self-contained unit in here with everything contacted up on the top side. Okay. Now, those are all very nice pictures, but when you come down to it, here's a silicon germanium transistor cross-section, and here's our emitter, base, and collector. And I put this up there just to indicate that there's a lot of complexity associated with building those in a modern integrated circuit. And there are a lot of interfaces with other materials in here. So this is, instead of being isolated with this PN junction here, this is isolated with a trench that's filled up with silicon dioxide. So a lot of interfaces between different materials in an actual device that is using modern technology. So this is what we said we were going to do. This is our the way we understand the bipolar transistors. By turning on this diode down here with a base emitter voltage, so we put a positive voltage on the P-type, okay, and it's negative on the N-type emitter. So we inject holes into the emitter. That way electrons come out of the emitter. There's a lot more electrons in the emitter than there are holes in the base, so you get primarily electrons being injected in here. A few of them recombine with holes in the base, okay, so that the amount of the number of electrons that you get collected in the collector is less than you got emitted in the emitter. Okay, and so what we would like to do is know, well, how much gain did I get out of this? What's the benefit of doing all this? And you can express that as the ratio of the collector current to the base current. So that's beta, or the gain of the transistor. Okay, so we'll want to look at, well, what happens as a result of radiation. Well, probably one of the things that we'd be concerned about is if there were leakage between these junctions, if the base current went up so that we had our gain go down, those sorts of things would be of concern to us. Okay. So we can do these kinds of plots for the transistor. Here we've plotted the emitter base voltage against the base and collector current. And so this would just be if you were going to do a plot of a diode, this is what you'd come out with. This is a semi-log plot, okay, and you see that for a little bit of base current throughout here, you get more collector current, and so the ratio of those two currents at any particular place along the VBE line gives you the gain of the transistor. So if you're familiar with diodes, silicon diodes takes about 6/10 of a volt to turn one on, 6 to 7/10 of a volt. So 6/10 of a volt is right about in there, 7/10 is right about in there. So it's in the region of kind of maximum current gain. And so if you plotted that current gain, the ratio of the collector current to the base current, you'd come out with something like that, where you have a peak in the gain characteristic. And often you like to design somewhere near the peak of that gain characteristic. Okay. So bipolar transistors in a nutshell. Now, the other type of transistor is a MOS transistor. Bipolar transistors were essentially controlled by the base current. MOS transistors are going to be controlled by the gate voltage. So everyone's heard about CMOS technology. This is a cross-section of a CMOS integrated circuit. Okay, so you have two types of MOS transistor. You have an N-type and a P-type. And the N-type, they're both built on the P substrate. So in the N-type, you put two N-type implants that are separated by a P-type. So what you want to do is control the current between those two. Okay. So initially, you start off, if you don't have any gate voltage, those are just back bias junctions, so you don't get any current. It's like the diode. Okay, no current can flow. As you increase the gate voltage here, you attract, if you put a positive voltage on here, you attract electrons to the surface, okay, and you make a small channel across here connecting the source and drain of the transistor, and so you can get conduction. Same thing goes for the P-type, the PMOS transistor. You introduce a well here, you still have the reverse bias junctions, P to N, P to N. If you put a negative voltage on here, you attract holes, positive charge carriers to the surface, and form a conduction path across there. Okay. So that's the traditional kind of CMOS technology. In modern technology, it turns out that holes, the positive charge carriers have about 3x less mobility than negative charge carriers. So to boost the mobility of the holes, the P-type charge carriers, if you compress the silicon, okay, the holes go faster. Okay, their mobility is higher. So in modern CMOS technology, you'll find that they do several different things. They can put in silicon germanium regions and things in there to compress the silicon locally and increase the mobility of the transistors. Turns out the N-channel devices, if you strain them, pull them apart, the electrons go faster. So in the most modern technologies, you find that they're strained for the NMOS and compression for the PMOS. If you look down from the top, okay, on this, okay, this is the way a logic cell is laid out. So the gates are these red materials here and here. Okay, the source and drains are shown in blue here. So two sources connected to the positive power supply, and the drain is connected to the drain of the N channels down here. And that's the way it looks as a layout. So the operation is just what we said. Okay, if you turn it on, put a positive voltage up here, you form a channel between these two so they conduct. So you start to get some conduction here. If you increase the gate voltage higher, then it starts to, it goes into the linear region. So it continues to conduct, and this is a region where the drain current and the drain voltage are pretty much a linear relationship, shown there. Okay, then you go up to a point where the channel pinches off. Okay, you've got so much voltage drop across the channel here that you don't get any more current, even though you increase the drain voltage, and you enter a region of saturation. Okay, so if you have several curves, then saturation is a function of the gate voltage. And this is what the characteristics look like from the standpoint of the regular operation of the transistor. With changing gate voltages, you get more or less gate current as a function of drain voltage, and you have several families of curves that go up as the drain voltage increases. Now, the part also has a subthreshold region. You know, this is a linear plot. Okay, in the subthreshold region, as you begin to increase the gate voltage, you attract charge carriers to the surface, okay, but their relationship to the gate voltage, the drain current relationship to the gate voltage, is exponential in this region. Okay? And so we'll look at that some when we start to talk about radiation effects, and we'll see that that subthreshold region changes substantially with radiation. And so if you were going to look at how much leakage that you had in a transistor, okay, you don't want them to leak because that increases your power. So right now these guys are not leaky at all. They're down 1E minus 13, 1E minus 10, depending on the voltage that you get. So as we'll see with radiation, that leakage comes up and can increase to the point where you get as much leakage as you do actual drive current, and then you have a severe problem with operation and power supply current. Okay, that's my attempt at bringing the MEs up to speed on electronics. I'm sure you got all that. Okay, so what happens to the electronics in the radiation environment? Well, we said there are several things. Okay, there's galactic cosmic rays, and there are protons, and there are junctions in our integrated circuit or in our device, and those are very energetic, and they can come along and strike that junction. Okay. If they do, they ionize the silicon all along that path. Okay. So you have holes in electrons, positive and negative charges created all along the path. And the depletion region, the boundary between the N material and P material, actually extends out along the track of the particle. So as the particle goes away, the electrons are attracted to the positive voltage, the holes are attracted to the negative voltage, and you get a transient current, okay? A spike of current that comes along. That's the basis for all of the single event phenomena. So you'll hear people talk about single event upset, single event latch up, single event transients, single event gate rupture, single event burnout, and just a whole raft of other single event phenomena. The basis for all of them is that ions strike through a junction. Okay, so the one you've probably heard most about is single event upset. If you have a memory for your computer and you've stored data in that memory, you store it as either a 1 or a 0. If you put it in a proton environment or a heavy ion environment, if you stored a 1 and you get one of those strikes, you're going to end up with a 0. Okay? If you stored a 0, you may end up with a 1. So you've upset your memory. The data that you stored is no longer there. Well, how does that work? Okay, so what I've done here is this is a latch composed of 2 inverters. Okay, so for my ME guys, okay, this is my NMOS transistor that we saw the cross section of. This is my PMOS transistor, and when I put them together, I have an inverter. Okay. If I put 2 inverters together, I have a latch. Okay. Now it's an inverter because if I put a low state on the gate of this inverter over here, okay, I have a low here, okay, a 0 voltage, okay. 0 voltage on the N channel is not going to attract any electrons to it. Electrons want to go to a positive charge. Okay, so this guy doesn't get turned on, but I put a negative voltage over here, a 0 voltage, with respect to the source of the P channel, then positive carriers get attracted to the channel, and this guy turns on. So he turns on and drives that node up to a positive value. So I've just turned that switch on. So that switch is on, that switch is off. Okay. Same thing on the other side. So I have a low here, a high voltage over here. So this inverter gets a high voltage. Okay. Its high voltage wants to attract electrons to the surface of the N channel. So this guy turns on, switch on. This guy turns off, switch off. And so I switch this down to the ground, to VSS. Okay. So I put a low, I got a high, I got a low, and that's regenerates around the loop. Everything's stable. Okay. Now what I've done is I've indicated those diodes that were associated with the transistors. Okay. Remember this. Okay. See, I had 2 diodes associated here. Okay. With the N channel, I had an NP diode. Okay. There are those diodes. Okay. Now I've put current sources around each of the diodes, indicating the direction of current if I were to get a single event hit on that particular diode. Okay. So the photocurrent associated with a single event strike always goes from N-type material to P-type material. Okay. So in this case, where I was setting in a low here, and I'm setting at a high voltage here, okay. If I get a strike on this guy, this current pulls that voltage down to ground. Okay. If I got a strike on this guy, I really wouldn't care, okay, because he's at a high state already, and all he would do is just pull that up to a high state, so no change. But this guy, if he gets hit, he pulls him down to a low. Okay. If I pull this guy to a low, well then I turn on this P channel, and that P channel drives this node to a high. It comes around here, drives this node to a high, and then this is low, just like this guy pulled him low. I've changed states. So where I was storing a high state, a 1, and I'm storing a low state. Okay, well, how does that actually look? This is a SPICE simulation for a latch. So typically if I get one of those strikes, it looks like a double exponential. And what I want to find out is how much charge does it take in order to flip that state. So initially I was at Q high, okay, storing a 1 there, and Q bar was low, okay, storing a 0 there. I had my transient come along, and it drove Q down low and Q bar up high. So if I integrate the charge that's in that waveform, then I know what the critical charge is to upset my latch. So if I know what the critical charge to upset my latch is, then I can figure out what the error rate is in terms of errors per bit day. How many errors am I going to have in my memory? Okay, so there's a little equation. You can do something a lot more complicated than that, but it boils down to this. Okay, there's a scaling factor. AB is the area of the critical node. Okay, so how big a target does a single event, does a heavy ion have to hit? Okay, and what's the collection depth? Okay, how far down in the material is it going to go? That's the LET, that's the DEDX of the ion that went through. Okay, and then if I know my critical charge, I can estimate what the upset rate is on my device. And those are the kinds of things that you need to know for your design. Is it a problem or is it not? And do I have an upset rate that's in excess of what I can stand? And if I do, what do I have to do about it? Okay. So if you look at this from an actual circuit standpoint, okay, here's a 4 meg SRAM up here. So this was taken to a cyclotron, heavy ion source, okay, and it was exposed to a range of ions with different LETs. Okay. And so what you get is a cross-section of the upset. Okay. So this is upsets per centimeter squared per bit. So let's say out here in saturation, well, let's say let's look around 50. Okay, that's where iron was. Okay, so an LET of 50. So an LET of 50, I get probably 7e minus 8 errors per centimeter squared per bit. Okay. So if I know how many bits I've got, okay, I've got 4 megabits. So 7e minus 8 times 4e6 is what? 28 e minus 2. So I get about 0.3 upsets every day on that memory for a particular orbit. Okay. Now you can put this information in terms of you can fit a Weibull curve to this, and this is the information that would go into Cream 96 or SpinBis that would allow you to calculate the number of upsets that you're going to get in a day or an orbit or a year or whatever on that memory. Okay, so that's single event upset. Most of radiation effects have to do not with the intentional device, but have to do with the parasitic devices. Okay, so in the MOS transistor, for single event effects, we weren't so concerned about the MOS transistor itself as we were the diodes that were associated with it, because they were going to get the strike, okay, and create the transient. Okay, same thing for latch up. Okay, here's I've done the cross section for a CMOS device. Here was our in well where we're going to make our P channel devices. Here is our P well over here. We're going to make our N channel devices. But if I look at that from the standpoint of parasitics, okay, what I have over here is I have P material, I have N material, and I have P material down here. I have a P, N, P. I got a PNP transistor. Okay, didn't mean to build that. It's just part of the technology. Over here, okay, I have my source. Okay, that's an N-type material. Here's P-type material. Here's the well is the N-type material. So I have an NPN. Okay, NPN. Didn't mean to build an NPN, but I built one anyway because of the technology. Now, if I look at those closely, I see they're interconnected. Okay. That the collector of my PNP is actually the same material as the base of my NPN. And the collector of my NPN is really the same material as the base of my PNP. Now, if I were to get a strike that came down through here from a single event, I would have a current generator that went from the N-type material in the NPN to the P-type material in the NPN base. Okay. If I look at it, if I redrew that, okay, so this guy is the same as these guys over here. Okay. If you're familiar with something called an SCR, okay, a thyristor, that's the structure of a thyristor. Let's say that my current source would go right here, be from the collector down to the base of that NPN. Okay. So I would drive current from the collector down into the base. Now, what did we say? Okay, that would bias the base of that NPN transistor on. Okay, so I would get current gain out of it. So this initial base current would get multiplied by the gain. Okay, so I would get current flowing down this way. That current would pull this node down, which would turn that diode on, which would drive current into the base of that transistor, turning him on harder, and the whole thing regenerates. Okay? So what happens is, if I plotted the voltage of that device, it would go out here, it would reach some breakdown, and it would snap back all the way over here after both of these guys got turned on. And so I have a very high current region at a very low voltage. Now, what my single event strike has done is, instead of having to traverse this entire characteristic, it's put me right back here along some load line, so that I have a very high current and a very low voltage. So I've turned on a path that I didn't intend to turn on when I built my CMOS circuit. Well, we're talking about a very low impedance path. And so instead of going through the logic that I intended to go through, it goes through the metallization and through this, and I have a good possibility of burning out my device. And so the metallization gets burned out, and the device doesn't work anymore. For space applications, upset's one thing, catastrophic burnout is something else. So when you're selecting parts for a spacecraft, make sure you don't select a part that will latch up. That's the worst thing that can happen to you in space, okay, is for you to latch up. And how you tell that the part's not going to latch up? Pretty much you have to go test it. Okay, now we could upset our memories. We could latch up and burn out our device. We could also have transient upset. Okay. What if you did something to harden these latches here? Okay, they could be. This is essentially a memory, so a D flip-flop. Okay. The way microcircuits are designed, okay, it is you work on some things in combinational logic, and you latch them into registers. And then you work on the next cloud of combinational logic, you latch them into registers. So that's a pretty good model of how any logic microcircuit works. Okay, it's a registered technology. Now, we kind of know what happens if we upset these guys. What happens if we strike something in the combinational logic? Well, like I said, I was going to run through some combinational logic. That's AND gates and NAND gates and ORs and things like that. Okay, and then I was going to register it in these latches. Okay. If I had one of those strikes come through, okay, it might look just like data. It could be a spike of voltage. Okay, for CMOS, Q equals CV. So if you have current, you drive it into capacitor, you get voltage. Okay, my single event transient might look just like that. Now, if it occurs not on the clock edge, I don't care, okay, because I was going to register my logic on clock edges. But if it occurs within the setup hold time region of that latch, then it gets latched in as data. So I have single event transient that's latched in and now becomes an error. Now typically there's more area of combinational logic than there is sequential logic, these latches, in the microcircuit. So you're concerned that, well, I thought I had things taken care of. I didn't have too big a problem with these guys, but now I'm getting upsets that get clocked in. Now, the faster your clock goes, okay, the more likely you are to have one of these single event transients get latched in. So here, what I think this is Benedetto down here did, he essentially looked at the clock rate and the voltage in a cloud of combinational and sequential logic like that. And too bad I can't see the bottom of that, but this is in, gets 500 picoseconds right there, okay, and so that'd be a nanosecond, 1.5 nanoseconds, 2 nanoseconds, I think all the way up to like 3.5 nanoseconds. Okay, well that seems pretty short, except what's your processor running at? Maybe a gigahertz. Okay, so a gigahertz is a period of a nanosecond. Okay, and that means half a period's 500 picoseconds. A whole lot of upsets that come along at 500 picoseconds. So you're in danger of having all of these single event transients swamp out your normal logic and creating a bunch of errors. Okay. Now, that's all digital. What about if I have an op-amp or something, an analog to digital converter? What happens if I get one of those strikes on a node in that? Well, most analog circuits have high impedance nodes associated with them. So if I get a strike and create a current transient and discharge one of those high impedance nodes, it's going to take a long time for it to recover. So you see the time scale down here is in terms of 50, let's see, it's 50 microseconds, so it's 55 microseconds, 60 microseconds, 65 microseconds. So that's like 15 microseconds of transient associated with a single event strike in an op-amp. This is LM124. Okay, so you may have to design around transients that occur as a result in your analog circuit as a result of single event strikes. Okay. Now, there's also power that has to be managed in satellites, and we like to manage that power with power MOSFETs. What if I were to get a strike on the power MOSFET? Well, two things can happen. I can either rupture the gate or I can burn it out. Okay. Here's a schematic of the power MOSFET. Okay, so where in my CMOS I had my source and drain that were just in line. In the power MOSFET, what you have is the source, that's the end material, and you have the drain, the other end material, down here. So the current flows down and out. Okay, and I do a diffusion, implant in a diffusion So here's my P channel. Okay, so I want to create with my gate, I want to create a channel through the P material, and then I modulate the source to drain flow. Okay, if I have this guy turned off, and I get that ion strike down through here, then my electrons, they like to go to a positive voltage. My holes, they would like to go out to ground, but they're cut off by this P implant and diffusion. So they linger around here. I've got a voltage on the gate. I've got more voltage due to the Q equals CV kind of problem associated very close to the surface of that power MOSFET, and I can rupture the gate. Okay. So I have a short through the gate now. So I've shorted out one of the cells in my power MOSFET. Okay. How about if I don't hit through that direction? How about if I come in and hit over here? Okay. Well, you notice when I built my power MOSFET, I also built a bipolar transistor. Okay. So you see they've indicated that here. Here's what I said was my source, and there was my body, and here's my drain down here. Well, the source looks an awful lot like an emitter. Body looks an awful lot like a base, and the collector looks, and the drain looks a whole lot like a collector. Okay. So if I get a heavy ion strike that comes down through here, I get base drive into this transistor. And since I have base drive, and these things run at very high voltages, I can get avalanching of that base collector junction. And when I do that, I get into a thermal runaway condition, and I burn out that segment of the power MOSFET. So, you know, what do you do about that? Okay, you got to have power devices. If you look at the spec sheet, this is from International Rectifier. What they have done is they've gone through, and for their parts that are rated for single event effect safe operation, they've done a number of different ions and indicated the contours of drain to source voltage and gate to source voltage that you can use this device in and not be concerned about it burning out. Now that's all, you know, well and good, except you might have wanted to do your design out here at gate voltages of 15 or so, and that would put you in a susceptible region for burnout. So you have to restrict your design to that area. Power MOS transistors are very easy to burn out and very easy to have gate rupture. So if you're going to invest money in your satellite electronics, it would be well to buy rad-hard power MOSFETs. Okay, total dose mechanisms. I'm at an hour and 20 minutes. I would love to have something to drink. Why don't we take 5-10 minute break? Does that work? Oh, well, in addition, when you process it, okay. Yeah, yeah, possibly. Yeah, so that's part very simple. We have models, so like in that one slide I showed, there's an 88 model, 88 model. Those are models derived from data that they saw in different satellites. Those are actually processed in eyes because one question was, well, does it change the work? Yeah, it does. Yeah, so it's solar wind, mass ejections, all of those things. We did first changes, they change, so they have to update those models periodically. It's been quite a long time since we have changed. Well, no, it's very dependent on which solar party or issue. So Mars has no activities. Okay, so if you're going to Mars, you're going to get the solar wind, and that's going to be you're going to experience that. That's all the service that needs to be protected. And it's those has belts, and some of these orbit inside those reactions. That's what I thought. What's not free? So here I am. Usually a whole lot of something that's or it's smaller than height.
Yeah, I usually do it just Thanksgiving weekend is just starting. It's so fun. It's starting to be pretty cool. That's too bad.
All the water.
You didn't see anything?
Yes, yeah, but we lost that one. Yeah, so everything is shielded just is a matter of how much mass you have for what depends on strictly it is.
Yeah, it's too bad. I forgot to put it in. Yeah, I was playing for 1 year. I don't think it was in space for the week. So did you draw anything? I was like, doing space student. No, I pretty on 6. It's not fully sighted in yet. Before that, where I went out. But yeah, 6 is pretty.
Okay, is any of that making any sense?
And then another track, I wanted to shoot, and I think I got a little bit excited, and also
What he did on the show was to make this heavy less thick, alright?
Yeah. If you can thin the epi so that you bring the P substrate up closer to the top. So essentially, what you do is you short out, this resistor. Okay, if you short out that resistor, then you can't get a VBE on drop across there, and you harden it. Okay, the problem with that is you can only get it so thin, and as you get the epi thinner, see what you usually do is
my first 2 seasons, I only got here.
if you look at a profile. So here's your
and then I changed the back. Yeah, so there was 3 for like that 1 season. But anyway, then when I was cutting 3 times a
plus substrate, and you started off, and then you said, oh, okay, well, I'm going to make this.
So you're up to the reg, which is
but during processing, this guy output.
I could have.
Okay, so you started off with these at 3 microns, but he outdiffuses up here, and you're constrained because if he outdiffuses to the point that he hits that well, then you change the breakdown voltages as well. So there's a limit to what you can do. In fact, that this is outdiffusion here. This is still a fairly high resistance.
In 28 nanometers, for instance, that they have almost
Well, yes, I mean, when they go to 28 nanometers, they're most likely going to go to SOI. So you don't have, so why do you like to go to, one of the reasons you like to go to SOI is have a faster latch up. Okay, but you got the SOI material that collects low charge in there, so now you. I wasn't sure if I was supposed to pause it during there. Okay. All right. So we've talked about single event mechanisms. There are things you can do for single events. You can vote. You can do the triple modular redundancy thing. You can do error detection and correction. All of those things are fairly straightforward hardening principles. But if you vote, it's going to take you three times as much electronics. Error detection and correction is going to cause you some complexity, and selecting parts that don't latch up it will sometimes be a challenge. But having things fail on orbit is also a bad thing. So several opportunities to do things. Okay, my clicker is blinking. Does that mean you think it's going to go south? Do we have any batteries? Let's see if we got a couple of, looks like AAAs. Okay, let's progress on to total dose mechanisms. I told you before I forgot to introduce the concept of a rad before I showed you the rad versus shielding and orbits plot. So we'll talk about what a rad is here. Thank you. Let's see. Would you mind sticking those in here while I talk? We've talked about strikes from the single event from the heavy ions into the silicon material. And so up to this point, we've talked about ionization in silicon. Okay. For total ionizing dose effects, the issue is not, thank you, is not ionization in silicon, but ionization in the silicon dioxide. So silicon dioxide is what's been a convenient insulator in both bipolar and CMOS electronics. It's wonderful that silicon has a dielectric that's a very good insulator and very robust, but it has some issues under radiation. Okay, so there are several ways that you can ionize the silicon dioxide. We said that the solar wind and the galactic cosmic rays were made up of electrons and protons. Sometime when you've all heard of rim-scrolling radiation, so when you stop electrons in material, you can have breaking radiation that comes out as X-rays or gammas. So you have high energy particles that can interact with your spacecraft shielding to generate those ionizing photons. So for electrons, you can ionize material primarily through Rutherford scattering. That's a Coulomb scattering interaction with the electron coming in with the electron cloud around the atom. Protons can ionize both through Coulomb scattering, so that's a direct ionization, or through inelastic nuclear reactions. Now, protons do everything. Okay, electrons are massive particles, but they're very low mass. Protons are massive particles that are charged, and so they can generate direct ionization. They have a cross-section for nuclear reaction. So you can have a proton captured by an atomic nucleus, and the nucleus then becomes unstable and splits apart. And the two fragments from that splitting then recoil out and can create ionization tracks in and of themselves. The proton can also have elastic scattering with the nucleus of an atom and create a recoil. And so if it hits a silicon atom or a phosphorus atom or a boron atom, that recoils through the material and creates lattice damage. So protons do everything. For this, for right now, we'll talk about them as a source of ionization. Okay, gammas and X-rays. We said if you stop those in some of your materials, especially high Z materials that you have in the spacecraft, you can generate X-rays or gamma rays that also ionize. Now, we talk about ionization in terms of an ionization dose, and the units for that dose are rads. Okay, a rad is 100 ergs per gram. Okay, it's just a measure of energy, and if you're going to talk in rads, you have to say what kind of material you're talking about. So the same amount of radiation will deposit more energy in one material than another. That's the DEDX LET kind of question that we talked about before. So from a definition of a rad, rad's 100 ergs per gram, and that's the LET of the particle, okay, whatever, an electron, a proton, heavy ion, whatever the LET is. times the fluence times the scaling factor that takes into consideration the charge of the electron, so 1.6 times 10 to the minus fifth. Okay, so for all of the incoming particles, this shows protons and electrons, you can calculate how much dose that you get in rads from any of those particles given the LET of the particle, the fluence, and the scaling factor. Okay, pretty much a rad deposited by a proton, a rad deposited by an electron, a rad deposited by a heavy ion, a rad deposited by an X-ray, and a rad deposited by a gamma ray all have the same effect. Okay, within, certainly within the first order, all the same effect. So if you can specify it in terms of rads, you pretty well have it characterized. Okay, oops. Why did I quit looking? Not picking. Yeah, I mean, go like this. Oops. Maybe it's not the clicker, maybe it's the oops, there we go.
Use that for now.
Yeah. Okay. So when you have an ionization, you're going to create whole electrons pairs. That's what ionization is. So rad is 100 ergs per gram. That turns out to be 6.24 times 10 to the 13th EV per gram. In silicon dioxide, the ionization energy is 17 EV. In silicon, it's 3.6 EV. So if you know the density of silicon dioxide, you can calculate the number of whole electron pairs per rad silicon dioxide. Okay. So the reason I put that up there, there's a lot of whole electron pairs. Okay. Now in silicon dioxide, the electron mobility is far higher than the hole mobility. So the difference between 20 centimeters squared per volt per second versus 2 times 10 to the minus 5 centimeters squared per volt per second. So what does that mean? It means that if you have a field across your silicon dioxide, if you have a voltage drop across it, the electrons are going to go very fast, okay, within a few picoseconds out of the silicon dioxide. Okay, not going to be there anymore. They get collected in the metal electrode. They get collected in the silicon substrate, depending on what the polarity of the E field is, but they're swept out of the silicon dioxide. Okay, and this plot down here gives you an indication of the fraction of what do they call it? Of unrecombined holes if you have a strike by different materials. So if you have if you're exposed to gamma rays from cobalt 60, then those are pretty well diluted throughout the silicon dioxide material. They occur all different places depending on the Compton scattering that you have. If you have a ionization path from a fairly large particle, that becomes a strike through the material, then all of the holes and electrons are created along that column of charge that's being created. And even though the electrons are being sucked out, they're in the vicinity of holes and they can recombine. So you get a different yield depending on the type of radiation that you get. But the resulting deposition of energy takes that into consideration, so you still have, if you have a rad, it's a rad in any of the material. Okay. Oh, did you click it or did I? No, I don't know. Okay. Now, so we said our holes get left behind because they're very low mobility. Wherever they are in that silicon dioxide material, they get trapped in shallow traps. Okay. But with the voltage applied, they tend to hop from trap to trap to trap until they come to an interface between the silicon dioxide and the silicon. And at that point, they get trapped in quasi-permanent traps. Now, if they're trapped here, this is just a big capacitor. Okay. If they get trapped there, then they generate a mirror charge in the silicon. So just like a capacitor. Generate a mirror charge in the silicon. So if this is N-type silicon over here, it's just as if you had applied a voltage to the gate of the MOS transistor and you've created a channel between the source and drain. So you've had, if it's an N-type transistor, you've tended to turn it on. Okay. So independent of your applying a voltage or not applying a voltage, you have that trapped charge there, you're going to turn on the transistor, and then it's going to start leaking. Okay. Now, as we have, when I first started dealing with MOS transistors, we had gate oxides that were like 1,000 angstroms, okay, really thick. And that was a, we did all sorts of things to try to get away from this charge trapping at the interface there. But as technology progressed, the gate oxides got thinner and thinner. The voltages dropped, and the gate oxides got thinner and thinner. And what we found was, as the gate oxides thinned, they were less susceptible to total dose of radiation. Okay, just for this reason. Okay, the change in the threshold voltage required to turn on the transistor, it is the change in the charge that's trapped here, okay, the differential charge trapped, divided by the capacitance of the oxide. The charge that's trapped in the oxide is proportional to the thickness of the oxide. It's a volume thing. So if the area stays the same, the thickness changes, you're changing the volume. So the more volume, the more charge you have trapped. Okay. The oxide, the gate oxide, the gate capacitance is epsilon A over thickness of the oxide. Okay. So if you plug that back into the equation, Q equals CV, you find out that the change in threshold voltage is proportional to the square of the oxide thickness. So as I thinned that oxide down, my charge that was trapped decreased by the square of the gate oxide. So when I got down to about 100 angstroms of gate oxide thickness, my total dose problems with the gate oxide essentially went away. In modern technologies today, if you look at a FPGA or advanced processor or something like that, those are probably built on maybe 90 nanometer processes. The gate oxide thickness is 12 angstroms. Okay. So the oxide is so thin that you essentially have no problem with the gate oxide in turning on the transistor when you don't want it turned on. Unfortunately, gate oxides aren't the only oxides used in MOS transistors. Now, there's another thing that helps us, and that is that the charge anneals. Okay, this was trapped in fairly deep traps, fairly quasi-deep traps, quasi-permanent traps. But as time goes by, what happens when they get stuck in these traps? They get there's a trap there because there's a silicon atom that's bonded to 3 oxygen atoms, silicon dioxide. Normally, you'd say, well, he'd be bonded to 4 oxygen atoms, but at the interface, you tend to have these cases where there's not enough oxygen to go around, so you'll have 2 silicons that bond to each other, and that's kind of a warped bond. Okay, when my hole comes along, it can actually cause that bond to rupture, and this guy thinks that he's pretty well satisfied with having a hole there in place of having a bond to another silicon atom. Okay, but over time and temperature, as you get some thermal vibration at the interface, one of 2 things can happen. You can capture another hole down here, which makes him fairly happy, or you can actually have, you can shake that hole out and you can have this bond reestablished. In other words, it anneals. So if you put it in an oven, 100 degrees C, you wait about a week, have a chance for all of the atoms to vibrate around, you may find that the charge that you had trapped at that interface gets annealed out. And so your part comes back and it works just as well as it ever did. So what does that mean for space electronics? It means that if the dose was delivered in a relatively short time, like if I go out to a cobalt-60 source, I get around 100 rad silicon per second. It's pretty fast, because in space my dose rate is about a millirad a second. So that's about, 5 orders of magnitude different. So I got all my dose in a very short time. I got all that charge trapped in here. Okay, but if I anneal it, okay, and it anneals back, I have a pretty good chance that at a lower dose rate, the damage may anneal as fast as it builds up. So I'm often able to use parts that look like they had a total dose problem at a high dose rate at a lower space dose rate and have them work fine because they anneal as fast as they're damaged. Okay. Not always the case, you have to check it, but that's the reason that you get annealing effects that help you out.
How do you check that if I would do like that?
Okay. The way you check it, there's 2 ways. Okay. You could just leave it at room temperature. Okay. Bias it, leave it at room temperature, for a long time. Okay. So you could deliver your dose very quickly. Okay, and then anneal it for a long time on the order of that total dose spread out over the time that would give you a comparable rate to the space radiation rate. Okay, that takes quite some time. Okay, the other thing that you can do is you can put it in a oven. 100 degrees C is enough to anneal trap charge, but not generate interface states, which we'll talk about later. And if it anneals quickly within that week, you have a pretty good likelihood that it will be okay for space, especially if your mission is relatively short. So it gives you an indication of, okay, I can probably use this part, even though at the high dose rate it didn't look so good. So let's see. I think I just said all that. Well, I will say this now. As the gates got thinner, they also were more susceptible to electron tunneling into the trapped charge. So if you had that charge trapped next to the oxide, electrons can tunnel in to the oxide around 50 angstroms. So once we got down to 100 angstrom oxides, the thickness dependence of the oxide, coupled with the fact that you can tunnel in from the substrate and from the gate about 50 angstroms, means that you don't have much of an issue with gate oxides. So that's been a beneficial thing for us. Now, there's another problem that results from total dose, and that's the generation of interface states. So in the 50s and 60s, we couldn't make MOS transistors very well because of interface states. Interface states make the transistor move it further into enhancement. It's harder to turn it on. And so we had, when we grew silicon dioxide on silicon, we had all these dangling bonds, okay, where the two things don't really match up. You have the silicon crystal, you have the silicon dioxide, which is essentially amorphous, or tends toward being amorphous. And so the two lattices don't match up well. So you end up with having silicons with dangling bonds, and those are interface states. So they can trap charge carriers at the interface and runs the mobility. It's a big problem. So we couldn't get reliable MOS transistors in the 50s and early 60s until someone discovered that if you put the material in a high concentration of hydrogen, then the hydrogen would come along and passivate those dangling bonds so that you didn't have the interface states. And so that was the real enabler for MOS technology. Well, in radiation, the holes that are generated in the silicon dioxide can crack those hydrogen bonds at the silicon dioxide silicon interface. As a result of that, the threshold voltage moves more toward enhancement and the mobility is degraded, so the drive capability of your transistor, be it a N-channel or P-channel transistor, is greatly degraded, okay? And can be degraded to the point that the device doesn't work. So when you're evaluating the total dose performance of a MOS transistor or CMOS integrated circuit, there are two things that you have to be concerned about: oxide trap charge and interface states. So in order to bound those two issues, there is a military standard that requires that you do two tests. You do a high dose rate test, which gives you the majority of your trapped positive charges, trapped holes. And then after that, after you've done that, you subject the part to an anneal, okay, 100 degrees C for a week, for 168 hours. That anneals out the holes and leaves you interface states. So if the device works, okay, after the initial total dose exposure, and it works after the anneal, you've evaluated the two bounds of how bad the part could be. And you know that in your application that it'll be somewhere between those two bounds. And so that's the reason that you do a high dose rate exposure followed by an anneal to get both the trap charge effects and the interface state effects. Okay. Now, I said that we don't have a problem with gate oxide, really, because they've gotten so thin. But there are other oxides associated with the material. Okay, this is the way it's a pretty good representation of cross-section of the modern device. So you have your N-channel devices over here, you have your P-channel devices over here, and you have shallow trench isolation that separates the two. Now, the shallow trench isolation, this is filled with some type of dielectric. Most likely, there is a native oxide that lines the trench, and it could be filled with a glass, it could be filled with a polysilicon, whatever, but you have that native oxide that's lining it. That oxide is thick, so it traps charge, just like we were talking about the potential for the gate oxide. So you have charge that's trapped in here. So if you have positive charge trapped here, you induce negative channel along here, and so you leak from the source to the end well of the P channel. So you can see, even though you're in a very modern technology, very small feature size, you may find that the leakage current goes up substantially as you increase the total dose and trap more charge in here. Now, that's for bulk material. One of the things that people have done to get away from single event latch up that we were talking about, to make the devices faster, because to get rid of capacitance, is to go to silicon on the insulated material. Okay, so what they do is they come in and put a buried oxide layer down here, okay, and then they layer a layer of silicon on top of it, and make their transistors in that silicon on top. The problem then is that this buried oxide is quite thick compared to gate oxide, so it traps charges, and so you have leakage between the source and the drain on that, so you have another source of leakage. Over here, you have that source of leakage between the source and the end well. You also trap charge along this interface, because the polysilicon, the gate, comes up over that shallow trench isolation material as well. So that means that on the edge of that transistor, you have a channel that's induced independent of what you have, the voltage you have on the gate, and again it leaks from source to drain. So those are the mechanisms that are of primary concern in modern technology. It's not the gate electrode that's so much of a concern to us as it is these parasitic paths that have been made as part of the technology. Okay, that's MOS. How about bipolar? Okay. We don't have a gate oxide in bipolar, so maybe we shouldn't worry about that. But we do have oxides that are part of the isolation. So in our NPN transistor, recall we had everything was brought up to the surface, and we have to have oxide insulators between the emitter and base contacts and base collector contacts. It's that oxide in there that's the problem for us. It traps charge. Okay. So if you looked at your transistor, if you looked at gain as a function of emitter base voltage, okay, the same kind of plot we saw before. Okay, you start off with a nice, the PNP side. Okay, so this is the PNP side over here. And, you know, here you've got silicon dioxide insulator over the base material. So this is a lateral PNP. So you have the emitter, the base material is here, and the base contact's there, and then the collector is over there. So the current flow is in that direction. Or you can also make a vertical PNP where you have the emitter base region here, and you can pick up the collector down here in the substrate. Okay, the amount of area that interfaces between the silicon and silicon dioxide is, of course, different for each of those configurations. So for a vertical PNP, you start off like this after, I've forgotten, I think this is like a megarad. You've dropped the gain down substantially from the peak. It also dropped it very substantially at the low current levels. For the substrate PNP, it's worse than the vertical PNP, but not as bad as the lateral PNP, because the lateral has all of this surface area that's integrated, it's touching the insulator. And in all those cases, what's happened is that you tend to create interface states in these areas that causes the more recombination, and it increases the base current associated with the transistor. So you'll see in analog integrated circuits that you have some significant degradation in parameters that are associated with the gain of the transistors. Now there's another complication with bipolar transistors, and that's called the Elder's effect, extremely low dose rate sensitivity. A few years ago, about a decade ago, maybe a little bit more than that now, it was discovered that if you irradiated a bipolar transistor at a low dose rate, the damage was more severe than if it were irradiated at a high dose rate. So typically we like to irradiate at high dose rates, 100 rad silicon per second to maybe 300 rad silicon per second, because it doesn't take so long. But they found out if you came in and irradiated at a millirad a second or 10 millirads a second, the effect was much worse. So in this plot, what they've done is they've looked at transistors taken from several linear integrated circuits and looked at them at different dose rates. So this is the relative damage compared to the high dose rate of all of those different transistors. So you can see where if you're up here at 100 rad silicon per second, everything pretty much looks the same. But if you drop down here to 10 millirads or 1 millirad a second, then these guys, the PNPs in particular, have much more degradation than they do at the high dose rate. Now, the question was, well, is that indicative of what you would see in space? So there was a experiment done against about 10, 15 years ago called the MPTB experiment, where they took a number of devices. LM124 quad op amp was one of them, and they measured its performance in space, the solid line, and compared that to the total dose data that they'd taken at 3 different dose rates, a millirad a second, 10 millirads a second, and I think that's 10 rads a second. And you can see that the space response follows very well the low dose rate tests that were done terrestrially. So what does that mean? That means that if you're going to get a good indication of what your linear integrated circuit is going to, what its performance is going to be in space, then you need to test at a low dose rate terrestrially. So there are folks that have made a business out of doing extremely low dose rate testing. Now the reason for the difference in dose rate effects for bipolars is still an area of ongoing research. It probably has something to do with the development of space charge in the silicon dioxide at high dose rates as compared to not having that space charge occur at low dose rates. But there are other influences like the availability of hydrogen and the interaction of hydrogen with the dose rate process. But as of right now, there is no good way to predict which parts will have a Elder's kind of problem or not an Elder's problem. So some of the manufacturers have taken it on themselves, Intersil being one of them, to characterize their product line at low dose rates, so you can't get that kind of information from some of the vendors. Okay, then I'll say just a couple of quick things about displacement damage. I said protons can do everything. Okay, they can have single event upsets. They can have direct ionization. They can have nuclear reactions where the products come off and ionize or have single event issues. They can also create displacement damage through knock-ons. So here what you would see is the proton comes in, it has a knock-on with an atom, that atom recoils, and it hits other atoms and they recoil, and so you end up with a number of atomic clusters in your crystalline material. And what do those atomic clusters do? Well, they kill minority carrier lifetime. They're recombination generation centers. So that kills the gain of bipolar transistors. Typically not much of an issue in MOS devices because MOS transistors are majority carrier devices, so they're not affected much by changes in minority carrier lifetime. But any element that transistor, diode, optoelectronic devices that are sensitive to minority carrier lifetime and recombination issues are affected by this. And optoelectronic devices, LEDs and laser diodes have been particularly susceptible to those. And so here, this is a plot from Alan Johnson at NASA JPL, and plotting light output as a function of proton fluence. And you can see for some devices very significant drop-off in laser and light output. Those are particularly a problem in optocouplers. So optocouplers are used a lot in spacecraft to break the ground loop problems and do ground isolation. And so it's something that you need to be aware of. Okay, that's all radiation kind of issues. If you're flying your satellite and the part fails from radiation, or the part fails just because it wore out, it hit the end of lifetime, it doesn't make any difference. It still doesn't work. So a few years ago, I started looking at reliability issues that might be of interest to space systems. And one of the things that you note is that there are a lot of changes in the way transistors are made over the last 5 to 7 years or so. And so this kind of gives you an indication where we started off, kind of back 65 nanometers was kind of in the 2002, 2003 era. Okay, we had polysilicon for the gate material. We had silicon dioxide, silicon oxynitride as the insulator, and we had silicon as the material. So as we've progressed down here to 2012 to 2016, we're seeing a lot of change in the materials that are used and in the construction of transistors. So we've gone from bulk materials to the SOI materials that we talked about earlier, either partially depleted, very or fully depleted, very thin SOI material, or material that's on the order of half a micron or so, toward devices that are essentially the FinFETs, so where the gate comes up over the silicon material. So a lot of changes in the way transistors are made. Even significant changes in the dielectric, because we said for 90 nanometer and below technologies, the silicon dioxide is only about 12 angstroms thick. Okay. The thickness of a silicon dioxide molecule is about 2 angstroms. Okay. So if you drop one molecule out of that gate oxide, you've reduced the thickness of gate oxide by about 1/6. So it doesn't take much change to significantly affect the gate oxides at that thickness. And we had to stop at that thickness of 12 angstroms because any thinner than that, there's too much tunneling through the gate oxide, so the leakage current went up to so substantially that you couldn't stand the power drain. So in order to get away from that, there's been a move to high K dielectrics, so dielectrics with hafnium as the main constituent. And what you're able to do there is to make a thicker dielectric so that you don't have the problems with breakdown, gate rupture, and those sorts of things. So our friends at Intel went to this stack at 45 nanometers, so they went to high K at 45 nanometers. Folks at IBM have gone to high K at 32 nanometers, and it looks like that's going to be the dielectric for some time now. So in changing from 180 nanometer technology down to like 65 nanometer technology, if you look at just how much is scaling, everybody's heard of Moore's Law, where you just make the transistor smaller and smaller and smaller as you go along. That's scaling. But in order to keep the performance up as we've gone down, then we've had to introduce innovative materials and processes. So we went from aluminum metallization to copper metallization. We went from silicon dioxide interlevel dielectrics to low K dielectrics, so we could drop the capacitance. So you can see that in order to make each of these things work and have reasonable power budgets, it's been a requirement for a lot of innovation in the industry. When I first started working in this, the elements in blue were pretty much what was used, hydrogen and silicon and aluminum and silicon dioxide. In the intervening times, from the 90s through the 2000s, you can see that we're using the majority of the periodic table in developing these circuits. So a tremendous amount of variation in the way devices are made over the last 10 to 15 years. Okay. So as we've gone to those, this is the kind of Moore's Law plot. So we go down each step. Probably the workhorse technology now is 180 nanometers. The most advanced technology in production right now is 32 nanometers, and I think we'll see 28 or 22 nanometers perhaps in production by the end of the year. But you can see the progression of additional materials and changes in materials as we've gone down that line. Okay. So, what does that mean in terms of anything you can relate to? I like this picture because it gives you an indication of just how small and how much variability you have as you move from like a 50 nanometer gate length, which is probably the gate length that you have for a 65 nanometer process. By the time you get through processing it, it's probably about 50 nanometers. And as we move down toward like 22 nanometers, they are becoming just incredibly small. Okay. Now, that shrinking in and of itself leads to problems in reliability. So it becomes very difficult to make sure that you have uniform layers. You find that the materials, actually the electronic properties of the materials come into play. The sources and drains are so close together that you have tunneling from source to drain. We talked a little bit about tunneling through the gate oxide, requiring a change in dielectric material. The addition of straining materials so that you can get the mobility first of the P channels up and then get the N channel material mobility up even higher. So a lot of differences as we've gone through the different technologies. And it's not just the transistors that are changing. So it's quite typical to have 8 to 10, maybe even as many as 12 layers of metallization associated with some of the modern processes. This is just a cross-section of the metallization associated with the 8-level process. And you can see how incredibly intricate these are. So this is all copper metallization. Copper diffuses through silicon dioxide extremely fast, so you have to put barrier layer metal around all of the copper structures to keep capacitance down, because you can see there's a lot of parallel plate area in there that would give you a very good capacitor. So you want to lower the dielectric constant of the interlevel dielectrics so you don't spend all of your time charging capacitances. So a lot of changes even above the silicon layer. And let's see, I think I talked about the high K dielectric before, but it's not just a matter of throwing a high K dielectric in. There's a whole choreographing of the layer stack in order to get the gate material for the MOS transistor. And of course there are a lot of reliability issues that have to be addressed in each of those. Giving indication of the kind of variability we're seeing at feature sizes that are probably 65 nanometers and below. if you look at the distribution of threshold voltages, okay, we're used to saying, oh, okay, I'm going to design with the threshold voltage that's 0.8 volts or 1.2 volts or whatever. But as you go down to, in feature size, you see that there's a considerable spread in the threshold voltage. So the techniques needed to accommodate that spread in threshold voltage are very different than some of the design guidelines before. Matt and I are trying to do radiation-hardened, dirt-cheap electronics. We don't want to fight this battle. We've dropped back to 180 nanometer technology, so we don't have to worry about this. It's a plot of the standard deviation of the threshold voltage as you go down in channel length. And I've always liked this indication. This is an actual simulation of the implant process for a MOS transistor. The threshold voltage for the transistor is set by the doping concentration in this channel. And you can see that there's a lot of variability and spread. There's not all that many dopants in that channel, and there's fewer and fewer dopants as you go down in feature size. So probably the major reason for this spread in threshold voltage. Okay, so when you think about reliability, everyone thinks about the bathtub. Okay, this is infant mortality. Okay, so you buy something or you make something, you expect, well, there's been some foul-ups along the way. So you expect, okay, I'll have some guys drop out, but when I get those errors out of the way, then I should have pretty clear sailing, just a very low dropout rate until I approach the point where everything starts to wear out. Okay, so this is what's called the extrinsic reliability region, and this is the intrinsic reliability region. Now, what we see is that as we've changed down from 180 nanometers down toward 90 nanometers and now below, that this intrinsic reliability is moving to the left. So where, I don't know, 15 years ago, we had microcircuits that were made out of silicon dioxide, aluminum metallization, and polysilicon. Okay. All of those are very robust materials. Now we have the whole periodic chart of materials in there, and they are, and the processes that go along with them are less robust, and so our intrinsic reliability is moving toward the left. And where 10, 15 years ago, you could expect the wear-out time out here to be out maybe 30 to 50 years. Now we're talking about wear-out times of 7 years or 4 years or 3 years. Now, if you're building cell phones, you don't care because everybody loses their cell phone within 3 years and has to buy a new one. If you're designing satellites that need to be up for some significant amount of time, okay, 10, 15 years, this is a big problem. The two ends of the bathtub are driven by different mechanisms. Over here, are defect driven in the infant mortality area. We did something wrong. Okay, materials were robust, but we got dandruff in the DI water. We did something bad. Those are typically identified and hopefully weeded out in burn-in. So if you buy a circuit that's probably been burned in, and the attempt was to weed these guys out. then one would hope you'd have a useful life, and this is driven by just random defects that are very difficult to catch. And then the wear-out mechanism is a function of the materials and processes, their inherent reliability and ability to last over time in temperature. Now, when you talk about reliability and radiation effects, it's good to keep this in mind. This was for terrestrial reliability from single event effects. So if you look at typical failure rates for hard reliability mechanisms, so missing metallization, shorts between metals, that sort of thing, typically the industry is able to get that to between 1 and 2 fits. A fit is a failure in 10 to the 9th hours. Okay, so one failure in 10 to the 9th to 10 to the 8th hours. A pretty small failure rate. If you aggregate all of the failure mechanisms, the ones we'll talk about shortly, they probably fall in the 10 to 100 fit regime. Okay? But even terrestrially, okay, the result of atmospheric neutrons primarily, and alphas and particles that are part of the natural environment, without some kind of mitigation, you're talking about 10 to the 5th fits, and that works out to a mean time to failure of about 1.14 years. So that's the reason companies like Xilinx have farms of their FPGAs where they monitor those for upsets from terrestrial neutrons and other sources. So there's one in Denver, there's one on the East Coast, looking at changes in failure as a function of altitude. So the big gorilla in the room really are those single event effects that we talked about previously. Okay, so just a few things to talk about to introduce you to what the reliability failure mechanisms are that are important today. One of these that you're most likely to hear about is negative bias temperature instability. And that's a problem for, in fact, is probably the driving factor for reliability limits in most processes that are 90 nanometers and below. And as the name implies, it's engendered by negative bias and elevated temperature. So if you look at our inverter that we talked about before, the P channel, when it's on, it has negative gate bias. So the gate's 0 with respect to VDD. So any P channel transistor that's stable in this state, stable with the P channel on, is susceptible to negative bias temperature instability. It's aggravated by silicon oxynitride in the gate material, and you notice that the tendency is to move to hafnium for gate dielectrics. The only problem with that is that in order to get hafnium to work, there has to be an interface layer of silicon oxynitride between the silicon and the hafnium material. So found that devices with hafnium gates are still susceptible to this. The result of negative bias temperature instability is moving the P channel further into enhancement, so increases the threshold voltage and decreases the mobility and the drive capability. So if you had designed based on a propagation delay or drive capability of the P-channel to be something before it had experienced this kind of bias condition, it can change substantially over time. Okay, so I think that's just what I said. So here's the comparison of the original P-channel transistor. The threshold voltage moves over, so it moves further into enhancement. The number of interface states increase, so you get a change in slope here, and a reduction in drive strength, and an increase in leakage. Now, the mechanisms, there's a lot of controversy about what the mechanisms are, but basically it seemed to be very similar to the interface state mechanisms associated with total dose. Probably here a hydrogen ion from the material. Remember, there's a lot of hydrogen in semiconductor processes. It comes up and breaks this bond of the silicon atom that's passivated with hydrogen. The hydrogen is very volatile and begins to leave the vicinity and leaves this guy as a dangling bond up here that it is indeed an interface state. Now, since this guy is an ion, if you put a positive bias on it to drive him back down toward the interface, then the process can reverse. Okay, so that you have the hydrogen go back into the substrate, or the hole go back into the substrate. The hydrogen repassivates the dangling bond, and you go back to the same performance as before. So what you tend to see is that with the negative bias, you come up and have this degradation in the threshold voltage. You remove that degradation and it recovers. Doesn't recover quite back to the original, because you can imagine this is a statistical kind of process. And then if you kept doing this, it would repeat that over and over. So what you have is a time-dependent change in the drive capability of that transistor. And as I say, if you had designed based on certain drive expectations for your device, you're likely to fail timing. And I think I said all of that, same sort of thing as the picture before. You note that the NBTI problem becomes worse. The recovery is less as you go down to the smaller feature size. Okay, and I think I've been saying what the circuit and lifetime issues are. Changes in propagation delay, reduced noise margin in SRAMs, increased mismatch in analog elements. So if you have a differential amplifier in analog design, depending on what the stable bias is on one side with respect to the other, you may have NBTI problems in one side and not the other. And the only mitigation approach is to design for end of life, and that sacrifices performance. Okay, so that's NBTI. NBTI seems to be worse in P-channel transistors because they're the ones that typically have the negative bias. There have been positive bias temperature instabilities identified in N-channel devices, but seem not to be as prevalent. However, N-channel devices do have hot carrier injection problems. So what happens is, as you get narrower, shorter and shorter channel lengths, then the E field between the drain and source goes up. So carriers which are emitted at the source, okay, the electrons travel through here, they're accelerated by that E field, and then they experience impact ionization at the drain. So you whack into something, you generate a lot more carriers with high energy, and those high energy carriers, a portion of them tend to be injected into the dielectric material. So as a result, you generate interface states and changes in threshold voltage especially at the drain end of the transistors. And it's dependent on not only the gate voltage of the transistor, but also the drain to source voltage of the transistor. And similar sorts of things for in-channel devices, the threshold voltage increases, the mobility decreases, and you have additional ionization. I can't remember why I put the ion up there, but anyway, so you have a general slowdown of the in-channel transistor, and typically where you said, okay, the in-channel needs to be a factor of 2 smaller than the P-channel because its mobility is higher, then that matching is affected by the changes in threshold voltage and mobility, and it changes your propagation delays and performance. Hot carriers are extremely sensitive to the drain voltage. There is some annealing over time, but it's limited. So as drain voltage increases, then the lifetime due to hot carrier injection is substantially decreased. Notice this is a log scale, and so hot carrier injection is a serious problem. About 3 years ago, I went over to Alliance Analytical, and they had a job where they were doing a failure analysis for an avionics company. And the avionics company had built a new box, was full of SRAMs, and they had experienced failures in that box after like 6 weeks of being in the field. And so they brought it back in, they narrowed it down to one particular SRAM that was in there, and they sent it to Alliance Analytical. And what Alliance found was that there was a row of latches on one side, or a row of, there was a row of memory on one side of the SRAM that was all damaged. And so they went back to the manufacturer, to the board maker, and they said, you know, we found this position memory is the one that's always failing. We don't know why it's failing, but we'll tell you that. So they went back and they found that their software guys, when they had, they were writing health and status of part of the black box to a particular memory location. They wrote it every cycle. And so every cycle they wrote to the same place. Of course, why would you not write to the same place every time? And so they were getting hot carrier injection at those sites because they were just continually exercising. So parts fail and systems fail from hot carrier injection. Breakdown mechanisms, the gate oxides are extremely thin. We said if we lost one atom, we lost 1/6 of the thickness of the oxide. So what we've seen in recent years is not only do the oxides break down sharply, but there is a period of time in here where they begin to do a very soft breakdown. And you can see that in the noise performance of the transistors. So that's a particularly insidious problem because it's very difficult to detect. And with the thinning of the gate oxides, it's becoming more and more of a problem. It's very hard to pick that up in a screening. So basically, oxides break down through a percolation kind of process. So as you apply a overstretched voltage, you begin to have hydrogen percolate through the oxide. You probably see a common theme that hydrogen's often involved in several problems that we have, but it's also very necessary for the process. So as hydrogen percolates through there, it creates defect sites with oxygen, and those sites, as they join up, result in a short through the device. Now, for thick oxides, that was very characteristic of the dielectric strength of the material, silicon dioxide. But as we thin the oxide, it takes fewer percolation sites to bridge the two sides of the capacitor, and we also see that there can be tunneling. So let's say we didn't have the final percolation site, there's tunneling available from one side of the capacitor to that site. It's a result and results in our reduced breakdown and the soft breakdown. Now, the reason it's so hard to detect is that the transistor doesn't always catastrophically fail, and it depends on where in the transistor the short occurs. So this is a plot of the resistance through the oxide as a function of where that percolation site is. So if it's close to the source or the drain, okay, the resistance of the oxide drops down substantially. Looks like a hard breakdown. If it's over the channel, the resistance in the short is relatively high, and so the transistor can continue to operate. And as I say, it's very, very difficult to detect. And you see that in the reduction in the drive strength of the transistor over time. So again, affects the timing design of the microcircuit. Okay, well, that's all I know. Okay. In summary, all you guys that are involved in CubeSats and small sats, there's a high reliance on commercial parts. There are issues, both radiation issues and reliability issues associated with those parts. As you progress in your career, or perhaps to more complicated satellites and systems, radiation effects and reliability issues are something that you definitely need to consider. 6 months flight in a CubeSat, probably not too big an issue. You get less than 10 kilorads, and you're probably going to be okay. But as you move to longer missions, it becomes more important. I think you can expect to see increased variability in electrical characteristics as we move to the newer technologies. So it's going to be probably more difficult to design at the cutting edge of the technology. Probably going to have to drop back to something that's more stable. And I think there's going to be a continuing need for folks that understand the reliability of microelectronics and radiation effects, and I think that there are synergistic interactions between the two. And so hopefully in 40 years, you guys can do a presentation like this, and maybe there'll still be problems, so you'll have things to work on. Okay, so that's all. Any questions? Glad to try to answer. Okay.
You just have it on the. Oh, so it's got over here. Oh, look, we're multitasking. Stop recording. There.